Our earliest human records show that people have been fascinated with the heavens for thousands of years. Each civilization has reached as far as its knowledge and technology has let it. We're still reaching to Mars, Saturn, Mercury, Jupiter, and beyond. Today, satellite technology and revolutionary telescopes allow us to peer beyond our own galaxy to the very edge of the universe.
I'm at the center of a giant ear, a radio telescope that listens for sounds from outer space, ranging from the signatures of molecules in cosmic dust to messages from extraterrestrial intelligence. Canadian scientists have been at the forefront of much of this work. Tonight we take a special look at the revolution that has been made possible by radio astronomy.
About 50 years ago, scientists discovered the way to listen to the vibrations of the universe. Radio astronomy involves the detection of the vibrations made by atoms and molecules in space at their different radio frequencies, much like tuning a radio to different stations. Yet the radio astronomer is not listening in the normal sense. What he hears is no more interesting than the hiss of a radio tuned between stations. It may sound like this.
Every particle of matter in the universe absorbs and radiates energy within the range known as the electromagnetic spectrum. This energy may be broadcast as visible light, infrared waves, X-rays, or as radio waves. Radio astronomers like Dr. Alan Yen are interested only in radio emissions. They're not concerned with the sound itself, but with characteristics such as the power and wavelength of these signals. The signals may be emitted by distant quasars, galaxies, stars in the Milky Way, and by molecules in the space between the stars. Many of these emitting sources are hundreds of millions of light years away and arrive at Earth as very faint signals, so radio astronomy requires powerful, large-scale equipment. Emissions from these sources are collected in a dish-like antenna, focused, amplified, and recorded for detailed analysis and interpretation. Radio astronomy can penetrate the heavens well beyond the range of the optical telescope because radio waves pass through dust, cosmic debris, and the light of billions of stars that hamper visual astronomy.
You are locking on that at about 80, is it?
Using radio waves, astronomers from Canada and from countries all over the world are probing our galaxy and beyond. They're searching for explanations for black holes, pulsars, quasars, the chemical composition of matter in interstellar space, and to seek signs of extraterrestrial intelligence. They hope to determine how the universe began, how galaxies are formed, how stars are born and extinguished, and just where we on Earth fit in.
An important aspect of the radio exploration of space is the study of the chemical composition of the universe. Detecting these chemical components is a matter of tuning in to their radiation frequency. The first molecule in space was discovered in 1951. It was the hydrogen atom, transmitting at a radio signal of 21 centimeters wavelength, or 1420 cycles per second. It took 12 more years to detect the next molecule. Since then, many molecular compounds have been found, including water, ammonia, carbon monoxide, and alcohol. In fact, ethyl alcohol, the drinking kind, was discovered in a cloud containing a large quantity rated at 200 proof. The heaviest molecules found so far are known as the cyanopolynes and are made up of carbon, hydrogen, and nitrogen. They were discovered with the Canadian Algonquin radio telescope. The discovery in space of these compounds, water and the organic or carbon-bearing molecules, is a significant step in the study of the evolution of life. Ammonia is important because its elements, nitrogen and hydrogen, are essential in the chemistry of protein and the makeup of amino acids, which form the building blocks of life. So hydrogen, oxygen, carbon, and nitrogen are the components of all the molecules so far found in space, and are also the most abundant elements on Earth. They are the very chemicals that we are made of, the principal constituents of life on our planet.
To spawn life, organisms need a hospitable environment, a planetary home like Earth, and a stable star like the Sun as an energy source. It is probable that planetary systems like our own are common among the 100 billion stars in our Milky Way galaxy, as well as in other galaxies. Many astronomers believe that life has arisen spontaneously at different times and locations in these planetary systems. In the last decade, several radio astronomers have used antennae all over the world in a search of the universe for indications of intelligent life. One of the leaders in this search has been Dr. Frank Drake of Cornell University, who is the director of the Arecibo Observatory in Puerto Rico.
Everything we know says that there are many civilizations in space at all stages of development, some behind us, some ahead of us. We believe that by searching with radio signals, we can detect many of those which are ahead of us. If we could do so, we would learn from them many facts of science, of technology, of the sociologies that develop with time and civilizations, of the varieties of intelligent life that exist in the galaxy. And that perhaps is the most important thing of all, because it would tell us a great deal more about what the significance of human life, human intelligent life, is in this universe.
So far, using radio telescopes like this one at Arecibo and others around the world, about 50 million combinations of stars and radio frequencies have been searched for signals. Many of these searches have taken place here in the hills of this island in the Caribbean. Built into a natural valley, this is the largest single radio telescope in the world. It has a giant spherical reflector, 300 meters in diameter, creating a total energy collecting area of approximately 81,000 square meters. This dish, made of aluminum mesh, focuses radio waves to a receiver which is suspended above it, 50 stories in the air. The suspension platform weighs 540 metric tons and is 99 meters long, longer than a football field. This platform is so stable that it moves less than 3/4 of a centimeter in any direction. On the bottom of the platform are the receiving antennae, which are movable on a track concentric with the dish through 30 degrees. This mobility allows the telescope to collect radiation from different points in the sky. But how do we know where to aim the telescope?
The most common and obvious strategy is to search for signals from the nearest stars, which are like the sun. But there are some people who believe we should search the nearest galaxies, because then you test perhaps hundreds of thousands of stars at a time for intelligent signals. There have been many searches carried on. In fact, about 50 million combinations of stars and radio frequencies have been searched for signals. And right now, we're embarking on a program to expedite the search by building radio receivers which can monitor millions or even a billion frequency channels at once.
Also attached to the platform is a powerful transmitting antenna, which has a power output of 500,000 watts. When focused into a narrow beam by the reflector, it has an effective power of 20 million watts, 20 times the total power production of all the electrical plants on Earth. When used for radio transmission, it creates the strongest signal leaving Earth, and in the direction it is pointing and in its frequency band, This signal makes Earth one of the brightest stars in the galaxy. This power has been used in a showy but unique transmission, a message sent from Earth deep into space.
In November 1974, we intentionally sent a message which was designed to tell things about ourselves to other civilizations. This message consisted of 1,271 characters. It took 3 minutes to send. By the time we had sent the last characters in the message, the first characters were already passing the orbit of the planet Mars. It has been speeding outwards at the speed of light ever since. Already it's farther than the distance to the nearest star. It's still going at the speed of light. We sent it in the direction of the great globular cluster known as Messier 13, 25,000 light years from us. So it will take 25,000 years for the message to reach its destination.
The message is written in binary language and includes the atomic numbers for hydrogen, carbon, nitrogen, and oxygen, the formula for the components of the DNA molecule, the shape of the human figure, our population, the location of the planet Earth, and the shape and size of the Arecibo telescope which sent the message.
The chance of this message being received by another intelligence seems to be even less than our chances of receiving a message from space.
What do you think the chances really are of your intercepting a message from extraterrestrial intelligence?
There are perhaps some 10,000 or 100,000 detectable civilizations in the galaxy. There are probably many more than that, but that's the number we could detect with our radio telescope. Now that may seem like a lot, but in fact it means that the nearest civilization may be only 1,000 light years from us, and only 1 in 10 million stars may have a detectable civilization.
But if you're really truthful about it, your estimates are all based in the final analysis on acts of faith. Isn't that right? I mean, after all, we only know of 9 planets, the ones in our solar system. We only know of 1 planet with life, namely ours. So that couldn't you really be out by a factor of 1 million?
They could be out by a great deal. We think not a factor of 1 million. In fact, if you make the proper mathematical calculation, you estimate that the overall uncertainty is about a factor of 100. And indeed, the estimates are based on some things we don't know very well, such as the abundance of planetary systems. As time goes on, we will learn these better through conventional astronomical research. And of course, if we could find but one other civilization, we would greatly improve our knowledge of what the distribution and statistics and numbers of civilizations are.
A machine as large and yet as sensitive as this radio telescope requires constant tuning and maintenance. Designed by suspension bridge engineers, radio astronomers, and other specialists, this combination of structural steel, cables, aluminum, and electronics is subject to the effects of the elements. At the time of filming, Puerto Rico was threatened by a hurricane. This required taking apart the most sensitive and vulnerable antenna. As it turned out, the full fury of the hurricane did not hit the island, but winds did blow in 80-kilometer-per-hour gusts, enough to threaten the antenna. When the hurricane passed, the antenna was reassembled, and exploration of the clear Caribbean sky resumed.
Far north of Arecibo in Algonquin Park in Ontario, 480 kilometers north of Toronto, radio astronomers are carrying out another kind of research.
I see, okay.
Dr. Alan Yen of the Departments of Electrical Engineering and Astronomy at the University of Toronto and his colleagues are involved in a unique experiment that studies space and Earth at the same time.
It should be 10 megahertz off from here, so it should be here.
Has this group been involved at all in SETI, the search for extraterrestrial intelligence?
No, we have not, because we feel that extraterrestrial intelligence is quite a possibility, and there are people who are interested in that using this instrument. However, this instrument is not the most suitable one. You need a large collecting area, like a bucket, like in Arecibo. And then you can have better chances of observing these very weak, possibly very weak extraterrestrial intelligence.
As a scientist, do you think that the SETI program is something worth pursuing?
Well, if I'm a gambler, I would like to do that because you never can tell if you can find it. I think it's extremely important. But the chances of detecting it is extremely small. So it's a trade-off.
The amount of detail that can be seen in celestial bodies is directly dependent on the size of the telescope and the wavelength being examined. In other words, the larger the telescope relative to the wavelength, the greater the resolving power. The problem is that some radio waves are very long, so that huge radio telescopes don't have the resolving power of a large optical telescope. Several years ago, Dr. Yen and his colleagues pioneered a new technique that overcame this deficiency. By focusing two or more distant radio telescopes, approximately 5,000 kilometers apart, on the same quasar, and then linking them together, these scientists created a device the equivalent of a huge single radio telescope. It has an effective diameter equal to the distance between the telescopes. This technique is known as very long baseline interferometry. Now Dr. Yen and his colleagues are using a satellite, the Anik B, to link up three separate radio telescopes, not to study the heavens, but to examine variations in the rate of rotation of the Earth.
The new technique is really a technique developed for radio astronomy to look at extraterrestrial objects. However, it turns out that the same technique can be used to look on the Earth. Now, by look, I don't mean you really turn around and look at the Earth, but rather you still look out at astronomical objects, such as beacons or quasars.
What is the beacon?
You choose a strong natural object at great distance from the Earth. They may be of the order of a few hundreds of millions of light years. And these are objects, extremely powerful objects, which are likely to be quasars. And we don't study their behavior, no, we use them as a beacon, because we are really studying the Earth. Astronomers develop the instrument to study these quasars, but we turn it around to look at the Earth. Now, by looking at the difference of time of arrival of the signal transmitted by this beacon, arriving at the different locations, you can find the relative position of these points. For instance, we can find the distance across a continent to an order of accuracy of a few centimeters.
Well, where do satellites fit in all of this?
Well, because we have to measure very accurately the time of arrival of signals coming in from the quasar. So we need to know the clocks of distant observatories. We have to have accuracy of the order of millions and millions and millions parts of a second. You can say thousands of millions and millions parts of a second. And in order to do that, we make use of the satellite.
The Anik B satellite is being used in this experiment to link up three radio observatories, one in Algonquin Park, a second in Penticton, British Columbia, and a third at the Naval Research Lab near Washington, D.C. A clock signal from a transmitter at one observatory is sent to the satellite. The satellite relays the signal back down to small receiving telescopes at the other observatories. On arrival, this clock signal is compared with the local clock to determine the time difference of these geographically separate clocks to an accuracy of millionths of a second. Meanwhile, the large receiving antenna at each station is focused on a signal from the distant quasar. This quasar acts as a fixed point against which to measure relative changes in the position of each observatory, so indicating variations in the Earth's rotation. To measure these time differences, you look at the signal received from the quasar at one station and then at the others, then mesh them to find the time of coincidence and the variations, and that is the basis of the measurement.
But this is only one part of the experiment. How do these radio astronomy techniques help us to study the Earth? Involved in this aspect of analysis is Dr. Wayne Cannon, a geophysicist with York University in Toronto, who has been working with Alan Yen on this experiment.
or 2 dB doesn't make that much of a difference.
Wayne, when Alan Yen gives you his measurements, what can you then tell about the Earth?
What we're going to look at is its rotation and to try and determine the location within the Earth of the axis of rotation. The axis of rotation of the Earth is in constant motion. It doesn't turn like a wheel on an axle.
Simply, we can think of the axis of rotation as a line drawn through the Earth, about which our planet spins in a counterclockwise direction. In reality, this axis is not fixed, either in relation to the Earth itself or to space. There are two kinds of movement of the Earth's axis. In relation to the fixed stars in space, the orientation of the axis is continually changing, much like the movement of a top as its spin begins to decay. This motion is accurately predictable. Secondly, in relation to the Earth itself, the axis of rotation is also moving. In terms of the fixed coordinates of longitude and latitude on Earth, the axis constantly changes position. This polar wobble is not easily predictable.
The long-term changes in rotation rate are caused by fluctuations in the fluid in the Earth's core and also tidal interaction with the moon, which is causing the Earth to spin slower and slower.
I see.
But we're particularly interested in the short-term fluctuations in this set of experiments, which are related to weather systems on the Earth and changes in the oceanic currents. And it may be an important method of determining changes in the angular momentum of the ocean and the atmospheres. Why that's of interest geophysically is because the oceans are the dominant factor controlling climate on the timescale of years. To correctly predict weather 3 months ahead, you'd have to know what the oceans are doing. So that's a global problem. You can only, and the other problem is from surface measurements of the oceans, and you don't know what the material in the water is doing at depths. So this measurement only, of course, gives us the what's called the zonal circulation. That is the amount of circulation that occurs in a plane parallel to the Earth's equator. The ocean currents are, of course, much more complex than that.
Do you think these kind of data could be useful in predicting earthquakes?
Yeah, in fact, it's likely to be the case, at least for large earthquakes. There's a lot of indication that even the present method of determining the location of the Earth's rotation axis, which are going to be lots less sensitive than these methods, there's indication in that data that earthquakes have affected the location of the Earth's pole, and there's even some indication that the location of the Earth's rotation pole moves ahead of the earthquake, that is, a few days prior to the earthquake, which is an interesting possibility. The idea being that when the earthquake occurs, it strains all the material of the Earth and changes what's known as the moment of inertia of the Earth, displaces rotation axis. And the global strain field may, in fact, be set up before the actual local rupture occurs, so that the rotation axis is moved before the earthquake occurs.
Scientists believe the San Andreas Fault in California is a threatening weakness in the Earth's crust. They wait for something to happen. The sudden violence of Earth's internal restlessness has ripped apart cities and crushed human lives. Perhaps this experiment is a new step toward an early warning against the destruction of earthquakes.
It's a difficult experiment to do. First of all, technically, we rely on guys like Alan and so on to build the machines that can make the measurements. And then there are data processing stages beyond this, which are laborious, tremendously time-consuming. So from an experiment like this, it's usually typically months, and sometimes it's a year or more, before you actually get results from it. So these devices have revolutionized two areas now. They've revolutionized radio astronomy, in terms of studying quasar structure, but they're also revolutionizing geodynamics, the field of the motions of the Earth.
So by linking up these 3 radio telescopes in a technique that would normally be used to study bodies in space, we are on the threshold of a method of understanding, measuring, and predicting geological events on Earth. As Wayne Cannon, Alan Yen, Frank Drake, and astronomers at radio observatories all over the world explore the distant reaches of the universe, we are learning the mysteries of space and about our home, the planet Earth.
Radio astronomy is a science that requires much international cooperation. It is a science that reminds us that while people differ in language, religion, customs, and race, in the universe, we are in fact one tiny pair of eyes and ears, looking and listening. In reaching out into space, we are seeking knowledge about the cosmos, answers to questions about the origin of life, and indications that in a spiral arm of the Milky Way galaxy, we may not be alone.